And hopefully everybody's hear me. Okay, so how many of y'all have had complex analysis? Anybody? Just a couple. Okay. So this talk will be pretty elementary. We're not going to do anything like super duper deep or anything like that. But let me start with. So when I talk about a complex number, I'm talking about a number. I usually write Z for shorthand. It's A plus BI with A and B real numbers, right? And some of you have probably seen this, there's a couple of sort of standard ways to write a complex number. This is one of them, right? In coordinates like this. Another one is to use the trigonometry that I promised. So you can think of this point in the plane, right, where the x coordinate represents how far over to go with the real value, and the y coordinate is the b part is the imaginary value. I hate that terminology, but there it is. And this just takes you back to old polar coordinates from trigonometry or Calc 2 or something like this. You have this radius, and you have this angle here, theta. And so this A plus BI can now be measured another way. And you can write this as REI theta. How many of you have ever seen this representation before? And this comes from a very famous equation. Now, if you had a really good trigonometry, you might have actually seen this at some point. You can also derive this just from power series, right? How many of you have seen this from the Calc 2 days? How many of you have seen these power series, right? This is somebody probably beat this over your head with a 2x4 in Calc 2 at some point, right? And so if you just suspend belief like you're a physicist or something and plug in I theta here, right, to this power series, it naturally kind of spreads out into this. You get cosine x plus I sine x, right? Or cosine theta plus I sine theta. So that's another way to do this. But this is kind of a big thing for us. We have two ways to represent a complex number. You might choose to pick on sort of a Coykendall representation where you look at the real part and the imaginary part, or you might think of it as how far are you away from the origin and what your angle is, right? Notice that your angle is, in a certain sense, you might sort of think the angle is well defined, it's really not, but there's a couple of things to note here. Number one, notice if R equals 0, the angle doesn't matter anymore, right? And number two, the angle isn't really well defined, right? Because, for example, what's the angle here? Well, the first thing out of my mouth would be 0, right? But isn't it also 2 pi or 4 pi or 6 pi and so forth and so on? And so notice that if you put any multiple of 2 pi in here, right, then you get the same thing out. E to the I 0 is 1, but that's also e to the I 2 pi, e to the I 4 pi. So this is actually going to come up when looking at complex numbers and haunt us a little bit later. So let me take you through a couple of functions here. So I'm going to start off with a classic, the exponential function. Now, what are you used to with the ordinary exponential, right? With the ordinary exponential, you're used to this function being positive, right? Always positive, the x is never negative, right? And it decays to zero as you go to negative infinity, but never quite gets there. And it grows really fast as x increases, right? What happens to this if z is a complex variable? So let's write this in the classic form. E to the x plus iy. This should be e to the x, e to the iy, which notice, by the way, the complex magnitude of this is always 1, right? If you multiply this by its conjugate, you get cosine squared plus sine squared, which is 1, right? So if I look at this function here, complex plane, the real part sort of controls the size, if you will, right? Because this thing always has magnitude 1, right? So really what this equation is speaking to me, there's those voices again, and what it's saying is e to the x, or this e to the z, gets very, very large if x is large, right? So the real part controls the size of it. And of course, if x is a very, very large negative number, it's very small. And this thing sort of controls the angle, if you will, right? So notice it's got a little imaginary part. So for example, in the complex plane, if y equals 0, so that is to say, if you're along this line right here, then that piece is 0 and that piece is 1. And so it's just the ordinary exponential. So if instead of on the complex plane, you just look at, along the real axis, it behaves like the exponential. What if you look at it what if you look at it right here? What happens along this line right here? Well, your x can vary from negative infinity to infinity, right? But now your y is pi, right? And so the imaginary part is gone, right? And so it's e to the x times -1. So actually, the exponential function e to the z takes along negative values along that particular horizontal line in the complex plane, right? You can adjust that as well. I pi over 2. So for example, if the angle is pi over 2, that's going to be 0. And along this line right here, it'll have totally imaginary values, right? So it's kind of an interesting twist. Now, I define the exponential. Let me also point out that it's pretty easy to verify just by getting on your horse and doing it, that the exponential function e to the z is never 0, right? Because this thing is never 0. It's got magnitude 1. And this piece right here is never 0. So the exponential is never 0. However, on the complex plane, the exponential can take on any value, any complex value, with the exception of 0. Now, I introduced this exponential so that I can introduce the log, because I'm going to use the exponential and the log to help me deal with the promised root functions. Now, what I would want is for the log to be sort of the inverse of the exponential. And in fact, some texts will actually sort of use this, define it this way. What about the log function, right? So as it turns out, let me call it something other than that. The way you want to get this so that it inverts things, and you can check this, is it turns out that for this to be the inverse, you want the natural log of z to be the natural log of the magnitude of z. So this is the r part. So if you write z equal REI theta, it's the natural log of the r part, which is, and here we're assuming that z is not zero. So this will be some positive thing plus I times the angle. Now, why do you want it this way? Well, let's just go through this. E to the natural log, the absolute value of z plus I theta. Well, the magnitude of z is just a real number. So what this will return is the magnitude of z times E the I theta. So this should get you back to your original z, because what this is doing is this is saying, okay, my original z, that's the size. So this piece specifies the circle it's on, right? How far it is from the origin. And this theta here tells me what the angle is. So this actually is the inverse function. Now, the fact that we define log this way, or have to define log this way, is kind of interesting, because you might have different values for the log, right? It depends on what you say your angle is, right? For example, if I want to take so let's just take this point. What if you have the natural log of 1? I hope that's 0. And in most standard measures it is. It should be the natural log of the absolute value of 1. But now you tag on the side, right? Well, the natural log of the absolute value of 1 is 0. And usually I might call that angle 0, in which case you would get what you expect. But if I call this angle 2 pi, it's also possible for the natural log of 1 to be 2 pi I. Let me give you kind of an interesting bit here. So what you should remember now is the exponential sort of functions the way that you would expect it to. The log has got a little twist that you need for complex variables. So the log of something is just take the ordinary log of how the magnitude of it and then figure out its angle I theta. And the reason we're going to do this is many times. So for example, with root functions, we might find it useful to write f of z is e to the natural log of f of z. Especially if f of z has variable powers in it, right? For example, or maybe not even variable powers. And we constructed the natural log so that it's the inverse of the exponential. So let me give you an example. Okay, that's a little bit twisty on the brain, isn't it? Right? Take the square root of -1 to the square root of -1. What is that even? And you know what? When I tell you the answer, it's probably gonna make you angry. It makes me a little angry every time I do this. So let's write I to the I as e the natural log I to the I. Right? The utility of doing it this way is the natural log, just like the ordinary log, allows you to bring down powers. So this is e the I natural log I. Now, at this juncture, I need to evaluate this. And so the natural log of I is the natural log of the magnitude of I plus I theta. Well, all right. Here's where I sits in the complex plane. It's on the unit circle, agreed? So this is the natural log of 1, which is 0, right? Because the magnitude of I is 1. That's how far away it is from the origin. And the angle, I don't know about you guys, but I call that power of 2, right? Agree? So if you do it this way, this is going to be natural log I but actually it's more than this because this angle is pi over 2, but it could also be what, 5 pi over 2 and so forth, right? In fact, it can be pi over 2 plus any multiple of 2 pi which is e to the negative pi over 2 plus 2 pi k. So for example, k equals 0, I to the I is e to the minus pi over 2, right? So in particular, it's always real, which is kind of bizarre, isn't it? Right? Okay, questions so far? Okay, so I promised root functions. And so I'm going to use this bit of machinery we developed to look at root functions. Let's start with, okay, now this is a function from, so this function is the inverse of x squared, right? But x squared, of course, is not 1, and so you have to take, classically, this is like this, right? Everybody's seen this, right? This is an old, it's not even defined everywhere, right? It's continuous on the closed interval from 0 to infinity. It's not differentiable at 0, even if it was defined on the other side. And actually, and it's got that kind of steep curvature, right? It goes down to infinity. By the way, we used to have a joke at the undergraduate school. When I first showed up as a freshman, the upperclassmen said, just make sure you're not a member of the square root club. You know what the square root club is? You're in the square root club if you take the square root of your GPA and it gets bigger. See, only in the math class, I tell that joke. Right, so here is f of x here. Now, how do we do this for the complex numbers? Well, let's call it z, shall we? This is e to the natural log z to the 1/2, which is e to the 1/2 natural log z, which is e to the 1/2 natural log absolute value of z plus I theta. And that 1/2 multiplies the whole kit and caboodle here. Now, I'm going to separate this out. When I do cube roots, I'll do this a little bit quicker. So notice that this part, really, this is just the square root of the magnitude of z, right? So just measure how big z is. That's a positive real number or 0, and it's the magnitude of this. So this is the magnitude of z to the 1/2. So it's just like an ordinary square root. But you modify it this way. Correct? So if you have f of z equals z to the 1/2, I can write this as the magnitude of z to the 1/2 times e to the I theta over 2, or cosine theta plus I sine theta over 2. So this does what you want most of the time. But see, notice that as I change these angles, right? If I change my array of angles in which this is defined, that changes things. So let's define angles here because we're going to need it. So, and I'm going to say that my angles theta are always between minus pi and pi. I could even say, let me just say that right now so I define it everywhere. Right. So for example, if I take, if z is 1, then the square root of z using this formula is 1 to the 1/2 times cosine, let's see, at 1, my angle is 0, right? So 0/2 is 0. And I get 1. And for example, if I take t equal to I, then the square root of I under this definition is the square root of 1, because the complex magnitude of I is 1, times cosine. Let's see, with this definition here, the cosine or the theta for I is pi over 2. So this should be cosine pi over 4. What's I sine pi over 4? And I get, this might be familiar to some of you, 1 over radical 2 plus I, 1 over radical 2. And if you square that, you'll see that you get I. Right, okay, so far. But what if we had theta between 3 pi and pi? Right? Now what happens is the square root of 1 is equal to 1 to the half times cosine pi plus I sine pi. Right? Because now the measured angle, in this case, the measured angle of 1 is actually 2 pi. And I've got to cut that in half. Cosine of pi is -1 and sine of pi is 0. So I get the other square root of 1, right? By changing my angle definition. And if you check this range for I, you will get minus this, right? You'll get the other square root of I. Right? So we've repaired the square root function, right? Now you can take the square root of everything. Agreed? But there's a problem. Does anybody knows what the problem is? I mean, you certainly can take the square root of anything. Let me point out something. I decided to go minus pi to pi to get the whole complex plane, right? But I could have gone correct. What's the difference? Well, the difference is this. Under the first definition, then angle we're finding square root -1 is pi. Everybody agree with that? So the square root of -1 in this case will be 1 to 1/2 times cosine of pi over 2 plus I sine pi over 2. And let's see, cosine of pi over 2 is 0, sine of pi over 2 is 1, and I get pi. Right? On the other hand, if I had decided to use minus pi here, so if I used it in the second case, then in this case, the square root of -1 is 1 1/2 cosine minus pi over 2 plus I sine minus pi over 2. In this case, I get negative I. If I agree. This means that this is problematic. It is true that under either one of these definitions, I've defined a square root for everything. There's a continuity problem. Because, for example, very close to here, the angle is close to negative pi. Very close to here, the angle is pi. When you make that jump here, you're jumping 2 pi over 2, right? And e to the I, 2 pi over 2 is -1. This means that when you jump over this, you've actually moved by quite a bit. You've changed the sign. I agree. So the problem is, yes, the square root is defined everywhere, but it's not continuous. It's continuous in any neighborhood, but it loses its continuity here. This is the way this is solved sometimes is you remove this line here, and you also need to remove origin if you want continuity in neighborhoods. But I'm not going to quibble about that too much. But you remove this right here, and what you've sacrificed is, well, now I can't take square roots of negative numbers, but I've got this thing defined on almost all the complex plane except for the negative x-axis, right? And it's continuous, right? Oh, but I want to take square roots of negative numbers. No problemo. Cut that out, right? So say that theta is between, let's say, whatever this is, 1, 2, 3, minus 3 pi over 4, and whatever I get, 5 pi. Oh, I got that wrong. I'm computing the wrong way. Minus 5 pi over 4, and up to 3 pi over 4. Right, and now this will be continuous everywhere except for this ray that I've cut out. Okay, any questions so far? With the cube root, it's similar. Yeah, a little bit more complicated, but not much. So if you look at the cube root function, this one actually is defined everywhere. But it's not differentiable at 0. It's got a vertical tangent there. Right. How do we deal with it? You can already, how do we take cube roots for complex numbers? Well, it's the same way. E to the natural log, c to the 1/3. And I won't go through all the computations again, but this basically turns out to the magnitude of z, whatever the size of it is, to the 1/3 power, times cosine theta over 3. Now let me give you a short application of this. Some of you have seen, how many of you have seen how to find nth roots of unity by putting like a little regular n-gon inside a circle? Everybody seen it? Well, here's kind of another way that's similar to this. So magnitude c to the 1/3 power, cosine theta over 3 plus I sine theta over 3. So let's look at the cube root of 1. Well, I know one of the answers to this for sure, right? Well, 1 should be one of them. The outcome can depend on how you pick this. So if you declare let's say, let me see one here. Then 1, the number 1 is at theta equals 0. That's the appropriate angle measure in this range. Agree? And so, in this case, 1 to the 1/3 is equal to magnitude of 1 to the 1/3 power, cosine theta 0 plus I sine 0, which is 1 times 1/3, boring, right? But if you pick the next choice of angles, say we have right, then at 1 theta is 2 pi. Everybody agree with that? And so now what you get is 1 to the 1/3 is the cube root of the real number 1 cosine 2 pi over 3 plus I sine 2 pi over 3. And this is 1, let's see, cosine of 2 pi over 3, I guess, is what? Negative by half plus I times radical 3 over 2. Cube that, if you cut it better to do tonight, and you will get 1. Okay. And finally, if you have theta is between 3 pi then the value of the angle here at 1 is actually 4 pi. Correct? And so in this case, okay. And this is minus 1/2 minus I radical. And check all of these, they all cube to 1. Any questions so far? Okay, so let me do kind of an application here. Let me do one little bit more meat on it. How would you handle something that looks like this? Well, one of the things that you could do for this one, you don't have to, is you consider this these two functions right here. And I'm going to come up here with a trigonometric identity that you probably haven't seen before. This turns out to be, if you go through the same business that we did earlier with square root, what you get is this can be written as z squared minus 1 to the 1/2 power, the absolute value of 1/2 power magnitude, times e to the I theta plus phi over 2. So doing exactly the same process over here, you get basically the same power of the function. But see, here we have two angles here as opposed to the other. And the reason is because this really has two chunks, right? This is sort of the square root of z squared minus 1, which has multiple values except as z equal minus 1, and this is square root of z minus 1, which has multiple values except as z equals 1. So really what this looks like is this is how you measure this function or evaluate this function, just like we did before. At minus 1 and 1, each of these separate ones is single value, right? And theta, I will take these both between 0 and 2 pi. Now, let me point out something that's kind of interesting. Just kind of for giggles. What that means is I am never allowing my value of theta to be either 0 or 2 pi. It has to be off of that. And by the way, theta, I guess, is the angle. So if I've got some point here, theta is the angle that's measured here, and phi is the angle that's measured here. Okay. Neither of these can they're always between 0 and 2 pi. Let me point out actually that these two overlapping right here sort of repair each other. It's pretty easy to show that as you cross this, you're actually continuous. Sort of the two cuts, the two things that you have to get rid of here repair each other. And actually crossing this is continuous, crossing this is not. And so it sort of repairs itself, which is kind of neat. But let me get to some interesting stuff here. Let's suppose, well, I didn't want this here. Theta. And let's suppose that what we want to do here is this is so let's use this here and let's look at f of I. Okay, so what happens if I just kind of blindly plug in I to this, right? I get -1 and -1, agreed? It's because I squared is -1, so I get like radical 1/2 times e to the I theta plus 3 over 2. Right. So this is going to be the magnitude is 2 to the 1/2. And in this case, if this is I, and this is theta and this is phi, what do they add up to? What does this angle and this angle add up to? 180. That's exactly right. So the angle here is pi. So these add up to pi. And e to the I pi over 2 is going to be, well, of course, that's cosine theta plus I sine theta, so I get I radical 2. But now, let's apply the same function and let's do something with more teeth to it. And hopefully you'll see the pattern of this because you can generalize what I'm doing here quite easily. So let's try this with, what did I make up here? Z equals 2 plus 5i. Okay, let's just see what happens. Well, one of the things I can do is, let's just go straight ahead. Notice that Z plus 1 is 3 plus 5i. Z minus 1 is 1 plus 5i. And if I square this, or square, I'm sorry, if I multiply this, I get negative 22 plus 20i. If you just multiply this stuff. Right, okay with that. Okay, so how does that help us? Well, now f of z should be the magnitude of z squared minus 1 to the 1/2 times e to the I, well, or times cosine of well, let's see, 1/2 theta. Oops. Well, I'm just gonna write it out this way: e to the I theta plus theta. Okay, so let's kind of take this apart here. The magnitude of this, let's see, you know, square this and square this. So this is like 484 and 400. So this turns out to be 884. The magnitude of this, the complex magnitude of this is the square root of 884. And then you got to take another square root because it's to the 1/2. And this should be cosine of, well, let's try to measure these angles here. If we measure these angles here, and we have this 2 plus 5i, 2, so this is sort of like 0.25. Then this is what I think I call theta, and this is what I call phi, right? So I've got to measure these angles. This is cosine theta plus phi over 2 plus I sine theta plus phi over 2. Right. So how are we going to measure these angles? Well, theta is part of my triangle. That triangle is like 5 tall, right? And to go over here, this is supposed to be 2, masterfully drawn scale. So theta is actually the inverse tangent of what is 5/3, right? Everybody agree with that? And the phi is the inverse tangent of, well, 5. Correct? Everybody okay with that? So this is f of z, or f of 2 plus 5i, is 884 1/4 times cosine 1/2 inverse tangent 5/3 plus 1/2 cosine, that whole thing. 1/2 inverse tangent phi plus I times sine of the same thing. Everybody agree with that? So that's what this value function should be, this horrible, horrible thing. But there's another way I can skin this cat, because let's correctly take the square root of -22 plus 20i, which is the thing that we had in the square root. Okay with that? And the square root of this directly is 884 to the 1/4, because it's the same size again. But now we have, well, so now we're measuring from 0 because it's just the square root of this. So we have this -22 plus 20i. So this is 20 and this is 22 in length. So if I want to measure this angle appropriately, using inverse tangents and all, what I would do is, this is actually the cosine of this angle should be pi minus the inverse tangent of 10/11, right? Everybody agree with that? So this angle should be pi, take away the inverse tangent of 10/11, because I'm going to get this back in the right quadrant. So remember, we're taking half of this. So this is 1/2 pi minus the inverse tangent of 10/11. Plus I sine 1/2 pi minus tangent inverse 10/11 as well. Now these two quantities should be the same thing, right? Notice that we have a common sort of magnitude. That's a good sign, right? And since what's left over, these complex numbers, the real and imaginary parts must match, right? So in particular, what you have is that cosine of 1/2 tangent inverse 5/3 plus 1/2 tangent inverse 5 is equal to cosine of 1/2 pi minus inverse tangent 10/11. And that's only from comparing the x coordinates, right? So I compared the real part here to the real part here. I could get more if I'll compare the y's, but I'll just compare the x's from that. Now you got to be careful about this, because of course cosine is a periodic function. But as it turns out, oh, and I think that in both places here, let me circle this, I forgot 1/2. Looks like there's a 1/2 missing. So it turns out you got to be careful about this in general, but it turns out here that what you get is you get rid of the cosines and multiply by 2, and I get the following interesting identity. That's price. Right. Ever seen that identity? Well, don't ever say I never gave you anything, because you can vary this and just, you can really put somebody into a coma with this for sure. And let me show you another one. If you use, so here's one that I'll give you for an exercise to take home, because everybody should have a fun weekend. If you have, try this one. F of C is the cube root. So do this kind of magic and turn it into whatever you want, and take Z equal to 1 plus I. This is actually fairly easy. The three roots of this are 0, 1, and -1, and that's where you should make. So you should actually have three angles here. This one, and see if you can get this groovy little identity that comes out of this. Tangent inverse 1/2 plus tangent inverse 1/3 is equal to I over 4. That's probably not something you can count in a regular trig class, but it comes out of just what we did before, just comparing two complex things. Just for fun, kind of as one final corollary is take an angle here. I actually proved this another way because I was really intrigued by this. I've got great social life. If I have the angle tangent inverse 1/2, then that means this is 1, 2, this is radical 5. And if I have the angle tangent inverse 1/3, this is well, 1, 3 radical 10, isn't it? I actually wanted to verify this because what this says is this angle plus this angle should be exactly power of 4. Here's another way you do it. Take this triangle, scale it down to the size of this one, put it on there at a funny angle, and then, well, it should match up here, actually. Put it on there at a funny angle and see that measure is power of 4. You can also do it that way, just fine. So, but anyway, so that's fun and amusement with some basic complex variables. Any questions? Any questions? All right, the rule of the math club is all the pizza's got to be gone. So if there's still pizza left, be the hero of your dorm, take it home, eat it yourself, whatever. Y'all have a great weekend, and we will reconvene next week. Freeman Slaughter's going to talk, and that dude always has something interesting to talk about. Any questions? All right. Any questions out there, by the way, if you people can even hear me? Have a good weekend.